So today we learn another data structure about trees. So it's like, it's not the last lecture about trees. Next week we will have another lecture about trees. Persistence, segment, no, we talked about segment trees. You can do segment trees in persistent way. We discussed this when we talk about segment trees. So this lecture and the next lecture will be the last lectures about trees. And then we'll go to the end of the semester, we'll talk some another stuff. This lecture, this year we'll discuss Euler Tour trees. So what is this one? When do we need Euler Tour trees? Let's have some tree. This time we'll have not a directed tree, but undirected tree. So you have some tree. And it is not directed, so there is no some specific root of your tree, there is no some specific parents, ancestors and stuff like this. So you have trees like this. Let's have some multiple trees, some another tree. So you have some trees like this. And you want to perform three types of requests. First two types of requests are the same as in link-cut tree. So you have operation link and cut. Link UV and cut UV. And they are pretty much as the link-cut tree. So like in link-cut tree, link operation simply connects two separate trees. You have two separate trees, you have two nodes U and V, and you simply add an edge between these two nodes and just connect two trees into one big tree. So you add this edge, and now instead of two separate trees you have one big tree. And the second operation is cut. It simply removes an edge. So you have some, again you have some tree, you take some edge and remove this edge from your tree. When you remove the edge from the tree, you get two separate trees. Yeah? One tree contains node U, another tree contains node V. So it's like two reverse operations on a tree. One connects two trees into one, second is separates one big tree into two separate trees. So it basically acts the same as in link-cut tree, but this time since we don't have a specific root, we will allow these two nodes to be any nodes of your tree. No, actually, you can do it in link-cut tree as well. If you solve the home task for tomorrow, you know that in link-cut tree you actually can change the root of your tree. So if you want to connect two nodes which are not the roots of your tree, you can change the root of one of your trees to make this node the root of your tree, and then connect it using a standard link-cut tree operation. So basically, you can do these operations in link-cut tree as well. But the next operation is slightly different. In the next operation, what we want to do is to calculate some function on a tree. Let's go. And these functions, you want to calculate the function on a whole tree. So you want to take, like for example, if every node of your tree contains some value, you want to calculate like. Usually it is some commutative functions because you don't know the order of your nodes. Yeah? So in this function you calculate some function like minimum or sum or something. So like the sum of values for all nodes belong to the tree containing node V. So you take this node V, take the whole tree containing this node V, and calculate some function on all these nodes. Or edges, it doesn't matter. So you may have some values in nodes of your tree, you may have some values in edges of your tree, it doesn't matter actually. That's all. That's the whole plan. Now, again, you can do it using link-cut tree. It's kind of complicated, but you actually do it. To make this function in link-cut tree, you kind of need to, usually in link-cut tree you can calculate function on a path. You can combine the whole paths into one simple. So you can, for each node of your path, you can pre-calculate the function on everything which connected to this node, and then for this path calculate the sum of these sums, and in the end for this main path containing the root of your tree, you will calculate the total sum in the whole tree. But it's kind of complicated. So this time we'll discuss much simpler data structure, which allows you to make these operations. And it is the Euler Tour Tree. That's all. So let's go. So how to perform these operations? To perform these operations, we will do the same trick we did when we have LCA function. So when we calculate LCA function, we kind of transform the tree into a list by calculating the Euler Tour of the given tree. And we will do the same trick here. So for each tree, we will compute the Euler Tour of this tree, and then use this Euler Tour as a like a representation of your tree. Let me draw it. So you have some tree, let's say 1, 3, 5, 2, 6, something like this. So imagine you have tree like this. What I want to do? I want to find some Euler Tour of this tree. So I start from some node of this tree. Now let's take some node, like any node. Let's take node 1, for example. So you start from some node of your tree, and then iterate over all edges of your tree. Like if you double each edge, you will have an Euler graph, so you can build the Euler Tour. It's exactly like we did when we calculated the LCA in the tree. So we start from some node and like iterate. So go here, then go here, then go back, go here, go here, go here, go here, go here. And now let's just write all the edges we visited on this path. So we start from here. We visit node 1, 3. Then we go here, we take node edge 3, 5. Then we go back. Then we go here. Then we go here. Then go back. Then go back to 3. Then go 3, 2. Then back to 3, and then 3, 1. So this is the sequence of edges we visited when we perform the Euler Tour of this graph. So we start from node 1, and then we go here, 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 and that's the sequence of the edges we visited on this path. Cool. That's all. That's basically so this is a representation of this tree that we will use in our data structure. So now, how do we perform these two operations? No, let's start with some operation, let's say cut. So what happens when we have cut operation? So let's start from this operation. So when we need to cut some edge, for example, let's cut some edge 3, 6. Let's cut this edge. What happens? No, let's see. Our tree will be separated into two parts. So we have this part of the tree, and let's use another color, and we have this part of the tree. Yeah. I'm not sure if you can see the colors, but these two colors are kind of different. So for both these parts, we need to build an Euler Tour of this small tree. So how to build this Euler Tour? Well, let's see. What will happen? Let's start with it. So this Euler Tour is just the part of the whole Euler Tour of this big tree. So let's find the point when we go from 3 to 6. So here we go from 3 to 6. And now we walk into this second tree. So we'll iterate over all edges of this second tree and then go back. So the Euler tree of this part is simply the segment of this Euler Tour between these two edges. So between we go from 3 to 6 and back from 6 to 3. So here we go from 3 to 6, and here we go back. So the Euler Tour of this small tree is simply this segment of your Euler Tour. So when we need to build the Euler Tour of this part of this tree which we get after we cut this edge, we simply cut this part of the sequence, and this part of the sequence is the Euler Tour of this small tree. The second part is a little bit more tricky. So how to build Euler Tour of this part? No, we simply need to take this prefix. Yeah. Then we go to node 6. Then we iterate all edges inside this tree. Then we go back, and then we continue to iterate over all edges of the first graph. And what we can do is to simply connect these two parts. So we take this part plus this part, and we'll get the Euler Tour of the first tree. It's true. So we can connect tree from here to here because this node is the same. So here we have node 3 and here we have node 3. So we can simply take this part and merge it with this part, and we'll get the Euler Tour of the first tree. So when we make cut, we simply take this part plus this part. So the first Euler Tour will be 1, 3, 3, 5, 5, 3, and then 3, 2, 2, 3, 3, 1. So that's the Euler Tour of this part, and the Euler Tour of this part will be just this segment. 6, 4, 4, 6. Again, we just take, let me again write this. So these two parts, merge them into one big list. You have this Euler Tour. And you take this middle part, and it will be the Euler Tour of the second tree. That's all. So to make these operations fast, we need to maintain these lists in such a way that we can split this list and merge these lists. We can do it using binary search trees with split and merge operations like trees, like Splay trees, and so on. So each of these lists will be a, let's say, Splay tree. So each of these lists is simply a Splay tree. Let me draw a Splay tree once again. So so this list is actually not a list; it is a Splay tree. So these edges are in this order in this tree. Let's build some Splay tree. Let's say we have this 6, 4, and then in the left we have this 3, 5. Here we have 1, 3. Here, for example, we have 3, 6. Here we have 5, 3. So it's the whole left part. So now we need to make Splay tree of this. Well, let's have, for example, 6, 3 here, 4, 6 here, and so on. 2, 3 here, 3, 2 here, 3, 1 here. So this is representation of this list. And this list is representation of this tree. That's all. So we take this again. What's happening? We want to work with this tree. To work with this tree, we build its Euler Tour. It's here. And to work with this Euler Tour, we maintain this Euler Tour as a Splay tree, like this. That's the whole plan. And now, when we want to cut this edge, we take these 2 points in the Euler Tour, split our Splay tree in these positions, and connect them like this. Let's make some split. How to make split? So we need to make split before and after this 3, 6. So we take this 3, 6, make Splay operations in our Splay tree. So we need to splay this node to make splay this node. We make a zigzag operation here. So we have 3, 6. So 3, 6 will be here. So this will be the left child. This will be the right child. Yeah, like this. This will be the left child, and this will be the right child, like this. So I call this Splay operation on this 3, 6. Now 3, 6 is the root of the tree. I simply need to split before and after this 3, 6. So I just separate the left and right branches of this tree, like this. Something wrong. Yeah, this that must be here. My bad, my bad. Now, this tree represents this segment, and this tree represents this segment from here to here. Now we need to do the same with this edge 6 free. So we make splay of this node 6 free. To make splay, we need to make one zig operation, right? So we make a zig operation here. So 6 free is here. It's left, it's right, like this. So now 6 free is root of the tree. Again, we need to split before and after this 6 free. So we take the left branch is everything to the left, and right branch is everything to the right. So simply remove this, and that's all. So this tree represents this middle part, and this tree represents this last part. And now I need to merge first and the third part. So I need to make the splay tree of this Euler Tour. So I simply need to merge these two trees. To merge two splay trees, you take the maximum value in one of the trees. For example, in the left tree, you take in this tree you take the maximal element here. Make splay of this last element. So I splay this maximal element here. So it's 5 3. And now I simply connect this third tree to this first tree. Like this. That's all. And now I have two splay trees. One splay tree represents this Euler Tour. Second splay tree represents this Euler Tour. So this Euler Tour represented by this big tree. So it's 1 3 3 5 5 3 3 2 3 and so on. And second tree represents by this splay tree. Yeah. Again, I need someone to say everything is clear at least once in a minute. That's the whole plan. Now, how to make link operation? To make link operation, you need to do reverse operation. Let's make link operation. So what happens when you have let's make something interesting. So let's build some another trees. Let's have something like this. Yeah, good enough. So we have two separate trees. For each tree, we will build the splay tree, which represents the Euler Tour of this tree. This. So for this tree, let's say it will be 1 3, then 3 2, then 2 3, then 3 1. And for second tree, it will be, let's say 5 4, then 4 6, then 6 4, and 4 5. So we have these two Euler Tours. And now we make link operation. Let's say we connect these 3 and 6 like this. So we connect these 3 and 6. Now, how to build Euler Tour of the big tree? Well, let's just build it. So what happens when we try to make Euler Tour of this big tree? We will start with this node. We will travel along the first tree until we find this node 3. So we take some part of this tree which ends in the node 3. For example, this part. So let's take this first part. So it will be part 1. So we travel from here to here. Now we will go to the second tree and iterate through all nodes in the second tree. So then let me write it here. So first we use this part of the first tree. Now we take this node 3, 6, edge 3, 6, and go to the second tree. In the second tree, we need to iterate through all nodes starting from the node 6. So we take the part of this Euler Tour starting from the node 6. So we start from here and take this part of this Euler Tour. So we start from node 6 because we are now in the node 6. And use this part of Euler Tree to iterate through all edges in this part. So we take this 6, 4, 4, 5, this part. Now we are here, so we go here, then we go here, then we go here. Now we need to go back from here to here, so we use this part of this Euler Tour. To go back to node 6. So we use this 5, 4, then 4, 6. Now we are back to node 6. Then let me go from here, here. That's all. Now we iterate all nodes in this second tree. And now we simply go back and finish the first Euler Tour. So we go back to the first tree using node 6, 3. And then finish the Euler Tour of the first graph. So we start from the position when we finished last time and use this segment to finish the Euler Tour. 3, 2, 2, 3, 3, 1. That's all. That's the whole plan. And now we have the Euler Tour of the resulting graph, of the resulting tree. So again, how we construct this Euler Tour? We take the Euler Tour of the first tree, split it in position when we visit node U. So this node U, this node V. So we split it here. We take the Euler Tour of the second graph, split it in position when we have node V. So we have node V, so we split it here. Now we have these 4 segments, 1, 2, 3, and 4. And we simply use the segments as a constructor to build this whole Euler Tour. So we take this first part of the first Euler Tour, then go to the second Euler Tour, then take this fourth part, then use this third part, then go back and use this second part to finish the Euler Tour. Oh, that's a good question. How to find these split points? That's a good question. So all these operations are pretty fast. You can split and merge in log n time. The only trick is how to find where to split. So in both these Euler Tours, we need somehow to find these points where to split this Euler Tour. There are 2 solutions. One solution is do not need to change anything. Another solution is a little bit more tricky, but it's actually easier to implement. First solution, how to find these points. What you can do, you can take the node U, for example. So you can take this node U and find any edge connected to node U. So let me write it here. So you have this node U and this node V. You can take node U and find any edge connected to node U. For example, this X. And now in your first Euler Tour, you simply find this edge XU in this Euler Tour. Now, for example, here, if we take node 3, we can take edge 1, 3, find the position of the edge. Now, again, for each edge, we simply have a link to its position in this Euler Tour. So each edge have this pointer to this node. For each edge, we have simply the pointer to the node in the Splay tree. So you don't need to find the position of the edge in the Splay tree because you have the pointer to exactly the node of your Splay tree. So So you take this edge. For each edge, you know the node of the Splay tree corresponding to this edge, and you simply split after this position. And this place will be exactly when you have node u. So you take the Euler Tour of this graph, of this tree. At some point you have edge xu in this Euler Tour. And now you can simply split after this position, like right here. And it will be the position when you have node u. And the same way here, you can find any edge, let's say vy. So in this Euler Tour, in some place you have node u, y, v. You can split this Euler Tour in this position. Again, the whole algorithm is like this. You take the node. Each node contains the list of the edges. So you take the first edge from this list. You have this edge. For each edge, you know the pointer to the node in the Splay tree corresponding to this edge. And now when you have, so for node u, you take this edge. For this edge, you take this node and you split after this node. You can store all the edges in a map. You don't need this. No. You don't need this. So you can implement it like this. So for each vertex, you have a list of edges. I'll implement it in Java way, mostly. List of edges. Like this. And for each edge, you simply have the pointer to the corresponding node in the linked tree, in the Splay tree. Node. So this is node of Splay tree. Yeah. So you don't need any maps here. You just take the pointer from u to this edge and pointer from this edge to the node of the Splay tree. So you don't need any maps here. You just use these pointers to make this in constant time. These edges also have to be deleted. Yes, you need to delete this edge. Yes, that's right. When you cut the edge, you need to delete this edge from these lists. You can do it. You can remove the edge from the list. No, you can use linked list. For example, in theory, you can use linked list here if you want to remove it in constant time. If you use vectors, you also can remove from the vector because you don't care about the order of these edges in this list. So if you want to remove from the middle of the vector, so if here you just use the array list like in Java. Yeah? So if you use array list and you have this edge in the middle, when you want to remove this, you simply swap it with the last element of the list and then remove this last element. So when you don't care about the order of the elements in the list, I simply use this list as a set, right? I need to maintain the set of the edges, and I maintain it in the list because I don't need to find anything. I need two operations. I need insert elements, remove elements, and iterator of all elements. I can do it using simple array list. Yeah. So when I add element, I add it as last element of the array list. When I remove element, I simply swap it with the last element of array list and then remove the last element. And that's all. But if it finds shares with linked list, yeah, that's not small details. You need to have pointers to this list. So okay, no. That's why I suggest another method. Yes. When you remove the element, you want to know the index of this element in this list. So for each element, for each edge, you want to maintain its index in the list of the edges of the corresponding nodes. You don't want to find the so finding the element in the list is pretty expensive. So you don't want to find elements in the lists. So instead, for each edge, you can maintain its index in this list. So you can easily find the index of the element using this pointer to the list. So it's possible. Using very simple data structures, you don't need any complicated data structures, but it's kind of tricky. Yes, you want to maintain pointers to here, and then back pointers and so on. If when you remove, you use this reverse pointer, and then use here to remove this. It's possible. So you can think about this as an exercise. It's a good exercise about actually just simple programming pointers and stuff. So it's possible to do all these operations in constant time using only simple data structures, only lists and stuff. So you don't need anything special here. That's kind of tricky. There is another way to do this. Let me show you another way to do this to make everything much more simple. So to make everything much more simple, we don't need this actually. So for each edge, we will maintain the pointer to the node. We don't need this list anymore. What we will do is to maintain the positions of the nodes. So for these Euler tours, we will maintain not only positions of the edges, but also the positions of the nodes. So for each node, we will remember its position in this Euler tour. And simplest way to do this is to add more elements to these lists. So let's add to these lists of edges also the nodes. So we'll have two types of elements in this list, edges and nodes. For example, here, we start from the node 1. Let's put node 1 here. When we go to node 3, let's write node 3 here. Then we go to node 2. Let's put node 2 here. Then we go back to node 3 and then node 1. So for each node, we can maintain its position in this Euler tour. So now instead of having these 4 elements, we'll have these 7 elements. So we have this list in this form. So we have this 1, then 1, 3, then let's say 3, then 3, 2, then 2, then 2, 3. We already have 3, so every node contains only one position. So if we visit node several times, we maintain only one position, any position. Then go back to 3, 1, like this. And for the second tree, we do the same. So we start from node 5. Let's say we start from node 5. Let's go to 5, 4. Then we have 4. Then 4, 6. Then we have 6. Then go back. Like this. And then we already have 4. We don't have number 4. 4, 5. And for example, in the end, we have 5. Because why not? We want to maintain any position of the node. So again, these two lists represent the Euler tours of these two trees. Each of these lists is represented as a Splay tree. So I just draw them as lists because it's easier to show. Yeah, but actually each of these two lists is actually a Splay tree. So we will be able to split and merge them. And now it's much more simple. So for each node, for each vertex, we will also remember the node of the Splay tree. So each vertex of this tree have some node in this Splay tree, and each edge have some node in this Splay tree. So now what happens when we want to link? So I want to link 3 and 6. I take this node 3, find the corresponding node of the Splay tree. So I use this pointer to have this node of the Splay tree. And now I take this node 6 and use this pointer to find this node. And now when I know these two nodes, I know where to split these two Euler tours. So I simply need to split like around this position, before or after, that doesn't matter. So I can split, for example, first tree I will split here. So I split the first tree here, have these two parts. And I split second tree here, have these two parts. Now let's split it after that, like just to make it the same. So I find these two positions using these pointers from the node from the vertex of the tree to the node of the Splay tree. And I split these two Euler truths just near this position, just before or after this position, doesn't matter. That's all. And now I construct this big Euler tour using these 4 parts. Again, I start from these parts, so I go from 1, then 1, 3, then 3. Then use this edge to go here, 3, 6. Then use this part to iterate over second tree, use this 6, 4, 4, 5, then 5. Then go back. Then use the back edge to go back to 3. And then finish this order of the first graph. So again, this is the first part, then we go here, when we take this part, then we take this part to here, then we go back, and then we use this part to finish the Euler tour. We found this trick when we tried to implement this, actually. At some point, we tried to implement this technique, and it turns out this is the easiest way to implement this. The code is really simple when you do it like this. So that's basically the whole code. So for each vertex, for each edge, you have the node of the Splay tree. And now when you need to make link, you use this pointer makes split, split, merge, 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 merge. That's all. So the code is really like 10 lines of code. When you have already your Splay trees or something like this. And the cut operation is the same. So when you cut the edge, you take the pointer to this edge, from this edge to the corresponding node of the Splay tree, and cut around this position. The only problem, the biggest problem of this algorithm is like this. When you make the cut operation, so you have this U, you have this V, and you want to cut this edge. So what actually happens that in this Euler tour, you have at some point you have UV, and then you have VU. And the only problem of this implementation is to find the the order of these two edges. So you need to find which of these two edges is first and which is second. I don't know how to make it very easily, but in my implementation you do it like this. You take this first edge, like any of edges, like UV, split your Euler tour here, then you have two Splay trees. One Splay tree contains this, one Splay tree contains this. And you simply find which of these two parts contains edge VU. Again, by making Splay of this node, you make Splay of this node, check of these two, which one of these two trees contains this VU. And then you make, then you need to make make if statement like this. For these two cases, you need to make like slightly different code. So if UV is in the right part, then you split this right part like this, and then combine this first and this third part. If VU is in the left part, then you make the same in the left part. So that's the most tricky part of this implementation, but all other implementation is very simple. Now, how to calculate the function? So that's how you make split and link and cut operations. How to calculate the value? Well, it's pretty simple. Since each of your tree is simply contained in a single Splay tree, when you need to calculate some function on a tree, you simply calculate this function using this Splay tree. So if you have values in the nodes, for example, so each of these nodes contains some value. So these nodes of the Splay tree contain some values. When you need to calculate sum of these values, you simply use your Splay tree as a segment tree, and for each node calculate the sum of your subtree. Then in the end, in the root, you will have the function on these nodes. If you want to calculate function on some edges, then you do the opposite. Each edge contains some value, and then you use the same Splay tree to calculate sum on all edges. The same way, just the implementation differs by when you have values in these types of nodes or in these types of nodes. That's all. So you can, if you want to try to implement this, it's quite easy. You just put neutral elements in all these positions. So you calculate, for example, when you calculate sum of all elements, you just put zeros in these nodes and real values in these nodes, and then calculate sum of all elements. Sum of all elements will be sum of these values in the vertices of your tree. Cool. That's all. That's the Euler Tour Tree. One of the coolest application of these trees is to perform the dynamic connectivity problem, to solve the dynamic connectivity problem. So you can use this tree to maintain the connected components of your graph. It's kind of tricky. I will not do it today because since I don't have much time. But one of the coolest problems when you use Euler Tour trees is when you learn how to maintain the connected components of your graph. So you have a graph, you add and or remove edges, and you want to check if two nodes belong to the same connected component. You can do it by maintaining the spanning tree of the spanning forest of your graph. So for each connected component, you maintain some spanning tree of this connected component. And you can use this tree just to check which connected component is to. So when you add the node, add the edge, you just merge these two connected components. When you remove the edge, you need to find another edge which connects the same connected components. So you can do it using Euler Tour trees, but it's kind of complicated. Previous lecture video is, all lecture videos are uploaded on YouTube. The link is in the description, like always. Yeah. Let's have one more topic. So, since we have, we have more time, so let's discuss one more topic. I didn't mention it in the lecture about LCA, but it's kind of important technique. One more important technique which we skipped when we talked about LCA problem is the Tarjan algorithm to find the LCA of. Let's discuss this algorithm now. So when we talked about LCA problem, we managed to solve this problem actually quite fast. So when we discussed the LCA problem, we managed to solve this problem in constant time using linear time precalculation. And it's pretty hard to beat this. Yeah. So let's go back to LCA problem. So we want to be able to calculate the lowest common answer of two given nodes. So this LCA of U and V. And it's simply you take this U, you take V, you take this part, so this node will be LCA. That's quite an important problem for whole tree algorithms. So it's used in many situations. You want to find this LCA. Usually it happens when you want to calculate something on a path from U to V. So if you want to look on path from U to V, Like if you want to find the distance between u to v, you want to find this LCA and then split your path from u to v into two paths. So when you go from u to v, you go from u to LCA and then from LCA to v. We discussed it like a few lectures ago. What I want to do now is to show you another algorithm, which is practically very important. So we learned how to use Farquhar-Bender algorithm to solve this problem in linear time recalculation and constant time for request for queries. But this algorithm was pretty complicated, so let's remember what we did to achieve this time complexity. We split, we take our tree, build a Euler Tour of this tree, then split it Euler Tour into blocks of size log n over 2. Then we build sparse table on these blocks, and then inside each block, since we have not so many types of this block, we pre-calculate for each type of the block all the requests. We have this pre-computation table, we have this big sparse table, and then we use this sparse table and this pre-computation table to make the request in constant time. Yeah? This short summary of one of the previous lectures. So it's kind of complicated, that's what I want to say. It turns out, in practice, there is much easier algorithm which achieve almost the same time complexity, but the constant is, so the algorithm is much easier, and you don't need all these complicated data structures, so the constant for your algorithm will be much smaller. So it's actually, in practice, it's faster than the algorithm we discussed there. So I'll talk about this. So it's called Tarjan algorithm, but Tarjan invented almost all algorithms, so it's one of the Tarjan algorithms. Let's go. One small detail. To perform this Tarjan algorithm, we need to have all the requests in advance. So imagine you have, it's called offline technique. So you have all these requests. So I have list of requests of queries, let's say. It's query key. Queries. And for each query, I need to find the answer. So I have, again, in this technique, we have these requests one by one. So we take the query, find the answer. Take the query, find the answer. And each query is answered in constant time. This technique is different. In this technique, we need to have all these requests in advance. So first, we have all these requests. What's the difference? The difference is what in this technique, we can choose in which order to answer these queries. Sometimes it's important. We already have data structures like this. So in some data structures, it's important that you have all the requests in advance, so you can choose the order in which you answer all these requests. That's one of these data structures. Ready? So let's go. What we'll do? We'll do very simple algorithm. So we have these pairs of nodes. For each, we will make one traversal of the whole tree. So we'll start from the root and make a simple recursive traversal of the whole tree, like depth first search algorithm. If you know how to, we'll discuss depth first search algorithm in the next semester. So it's mostly referred to the graph. In the tree, depth first search is basically traversal of the whole tree. So you make the recursive traversal of the whole tree. And when you make this traversal, we will answer these queries. So imagine you have this node UI here and some node VI here. So this is one of your requests. This is one node of your request. This is second node of your request. We will answer this query when we visit the second node. So we make a recursive traversal of the tree. So we start from the root. So this is the root. We start from the root and make the standard recursive procedure which iterates over all nodes of your tree. So we start from the root and recursively call for each child of this root and so on. For each node, we recursively call the same procedure for all children of this node. So we start from here, we go here, then go here, visit some base nodes, visit some base node, go back, visit some base node. At some point we'll visit node U. Then we go back, visit some more nodes, some go here, go here, visit something here, and then we'll find this node V2. It's abstract picture, okay. No, basically this is the part of the Euler Tour which ends in the node V, right? So we start from the root and make, find the Euler Tour of this tree basically, yeah? So first we visit node U and then we visit node V. At this point, we will try to answer this query. And that's the plan. So how to answer this query? First, we need to maintain this query for each node. So each node will maintain the list of queries which uses this node as one of the nodes of this query. So for this node, we will remember the list of queries connected to this node. For example, we have this query. So for this node knows, then we visit this node, we need to calculate the answer for this query. So each node have a list of queries which uses this node. Okay. So you can do it in pre-calculation time, right? So for each, you simply iterate all queries. For each query, you put this query into this list. You simply maintain this list for each node. You can do it in linear time. That's easy. That's easy. So now, how to answer the query? Let's take this node V and find all ancestors of this node V. So this node V have some number of ancestors like this. Now what we want to know is to find the one which of these ancestors is actually the ancestor of this node U. How to do this? Let's say, let's mark all the nodes which already finished this recursive traversal. So when we already finished the traversal of the subtree of the node, we will mark this node as black. So these nodes are black. So we already finished the traversal of these nodes. So these nodes are marked black like this. Yeah. So for these nodes, we already finished the traversal. So these nodes are marked. What we need to do is to find for this node U the closest unmarked ancestor of this node U. So if you start from node U, you see these ancestors are marked and these ancestors are marked. It's root. It's not interesting. Let's make it not the root. So you start from node U and go up until you find the closest unmarked ancestor, right? This closest unmarked. So what happens? You start from node UI and iterate for all its ancestors. This ancestor is marked, this is marked, this is marked, this is unmarked. So the first unmarked ancestor of node U is the LCA of U and V. So this node is LCA of U, I, and V. So that's the whole idea. So again, you make a recursive traversal of the tree. First you visit node U, then you visit node V. When you visit node V, you look on the node U. The closest unmarked ancestor of this node U is your LCA. Now, how to find the closest unmarked ancestor? We actually had the same problem in the home task last week. You can do it like this. You maintain the sets of the nodes with the same result. Let's happen like this. Let me do it. So you have this path. So this is node V. if you look on the nodes with the same result, so all these nodes have the same answer as this node. So if U is inside this set, the answer will be this node. So like that, let me show this. So if U is inside this set, yeah, the result will be this node. And that's what we'll do. We'll maintain these sets with the same result. Well, let's add. Actually, if U is this node, it's also the same. So let's add this node. For all nodes, if U is inside this set of nodes, the answer will be this node. And that's what we'll do. We will maintain these sets with the same result. This set are basically these trees, like this. So we'll maintain these sets. Each set knows the top node of this set. And now we simply need to check in which of these sets belongs to node U. So we look on the node U. If node U is in this set, then the LCA of U in V is basically this top node of this set. That's all. And now to maintain this set, we will simply use the union find data structure. So we'll use union find data structure to maintain these sets of visited nodes. And when we visit some more node, we'll just unite these sets. So what happens when you, let's show you here. So what happens when you finish the traversal of some nodes? You have some node, yeah. So node X. Let's use some more letters. So let's have some node X. When you start from this node, you recursively traverse all the trees, all the subtrees of this X. In the end, each subtree is some set. No, it's not like this. Or it's simply one big set, right? So when you finish the traversal of this node X, all nodes in its subtrees are actually marked. So all these nodes are marked. So these all are marked nodes. So if U is inside any if U is any of these nodes, the result will be X, because X is the closest unmarked answer of all these nodes. So all these nodes compose one set. So for all nodes in this set, the result will be X. Now, when you finish the traversal of X, you need to mark this X. So X is no longer one of the possible candidates. So you mark this node X, and now for all nodes in this set, the result will be the closest node above X. So you take the parent of X and just unite your set with the set of your parent, because for this parent is inside some another set. So for this parent you have some, so this is the closest unmarked node for your parent. So now for each node in your set, the answer will be the closest unmarked node for the parent. So you simply need to unite your set with the set of your parent. This is basically the union operation in the union find. So you make the union of your set and the set of your parent, and that's all. So let's write the whole code. So the whole code will be very simple. So first you iterate all queries, and let's do it like this. No, I will put this query in both nodes, so in the left node and in the right node. But when I visit left node, I will not answer. When I visit the right node, I will answer the query. So we iterate all queries. Yeah. I will take list of u and add v, and I will take list of v and add u. And because I don't know which of these two nodes is left, which is right, so I'll just add it into both lists. And now I simply make the recursive traversal, so I make the go of x. So now I have this node x, yx. Let's have v. It's two main nodes. So I iterate for all nodes of v. Yeah, right. First iterate over this list. So I will iterate this u list of v. If u is not marked yet, if u is not marked, then just skip it. No, it means that my node is the first one. So I want to find this u which is already visited. So I need to visit this u and then this v. So if u is not marked yet, it means that my node is actually first. So this v, this is u. So I cannot answer the query right now. I will answer the query when I visit the second node. And now if u is already marked, then I will just say result for query, no, let's make uv like this, is good enough. So this is the result of the query uv. No, you may also remember the index of this query or something. Yeah. You will find out all the details. It's not that hard. So the result of this query will be the top node of the set which contains node resources. Top node of u, like this. So this operation is simply takes the top node in the set. Again, you take this node u. Node u is inside some set. You need this node of your set. You can do it using union-finding structure, right? Like for each set, you can maintain the top node of this set. It's like minimum in the set or something. It's easy. Cool. And now simply iterate all children. So iterate. Let's say x. Shit. So sometimes I have this, sometimes I have, okay. Children of v. So I iterate all children of v. Call the same recursive procedure for this node. And then in the end, when I finished the traversal of this tree, I will simply unite these two sets into one. That's all. So that's simple. So that's the whole algorithm. What is the time complexity? Well, again, time complexity of the union is constant. Time complexity of this operation is actually inverse Ackermann function of ML. No, if you watch the bonus lectures, I kind of explained. No, in the first bonus lecture of the last semester, I kind of explained what this means and why the working time of the union-finding structure is inverse Ackermann function. We need to mark v in the end. Makes sense. Makes sense. Okay, so you can find like in the union-finding structure, you can find the representative of your set in inverse Ackermann function, and for each representative you can maintain the pointer to the top node of your set. So this operation is simply find operation in union-find. Find operation have time complexity inverse Ackermann function. So the whole time complexity will be something like n plus m alpha mn, like this. Let's compare to the in the previous lecture, we discussed algorithm velocity in constant time. Yeah. So if you look on the total time complexity, it will be n plus m, right? This time complexity is n plus m multiplied by inverse Ackermann function. So it's strictly worse than this, theoretically speaking. But in practice, this inverse Ackermann function is very small. So this inverse function is always not more than, let's say, 3 or 4 usually. So this inverse Ackermann function is pretty small, and the constant factor is pretty small because all operations here are pretty simple. So all operations are simple and asymptotics is good. So the real time of this algorithm is actually better than all this complicated stuff. So it's quite good in practice. In practice, you can just use this algorithm to find LCA of the big number of pairs if you have a problem like this. Also, if you watched the second bonus lecture of the last semester, you know that you can use the same technique like in union find data structure to make the link eval data structure. When you link elements of your tree and also calculate the function on a tree. And you can use this technique here. So you can take this link eval data structure from this bonus lecture and use it here. And it will help you not only find the LCA, but also to calculate some function. So using this link eval data structure, you can not only find this top node, but also calculate the function on this path. So you take the node U and calculate the function on the path from the root to the top node of your set. And using this technique, you can not only calculate the LCA, but also calculate any associative function on the segments or on the paths in your tree. That's all. So in the end, you can calculate LCA of any pair of nodes and also function on any path in the tree in this time complexity using this Tarjan algorithm.